Welcome to the Accelera Portable Stimulus tutorial. My name is Faris Kandakji. I'm the chair of the Accelera Portable Stimulus Workgroup. Today we are going to deliver another update of the Accelera Portable Stimulus tutorial. That includes updates from the work in progress standard itself. We had tried to listen to your feedback on previous tutorials from previous forums and avenues, and we have changed the format a little bit, so you'll see more of a flowing story, less transition from presenter to another, so we have two main presenters today. I'd like to start by thanking Tom Fitzpatrick for leading the effort to basically revamp this tutorial and simplify it, make it more flowing, and for the rest of the committee members who actually contributed to it very actively in the past few weeks and days, up to the last couple days leading to this conference. Thank you, Tom, and thank you, Adnan, for presenting today. In future forums, we'll have rotating speakers, so we'll have different faces from the work group. With that, I'll just leave the stage to Tom.
All right, good morning, everybody. So, portable test and stimulus, the next level of verification productivity is here. What we're hoping that you guys will take out of this is not necessarily that you will be able to go back home and start writing portable stimulus, although that would be nice. You should all have been able to download these, so if you do go through the slides, it should give you a pretty good idea of what it is that we're trying to do. But what we're really trying to do is kind of help you understand why we've been spending the last, 3 years, certainly of my life, trying to get this done. Keep that in mind, and we really want you to understand the why as much as the how. And that kind of goes for verification in general, right? We don't want to focus too much on the details. We want to focus on the intent of what we're trying to do, and we kind of want you to get that same feeling from those of us in the working group. So why are we doing all this? Well, we're living in an SOC world, right? So this is the results of a study that Mentor has commissioned Wilson Research Group to do over the last several years. These are the trends. So what we're seeing is that 72% of ASIC designs contain an embedded processor. Right? How many of you guys have embedded processors? Yeah, close to 3/4. The interesting thing about this is you'll notice that the percentage has been flat for the last 6 years or so, but the percentage of designs with a lot of processors is definitely increasing. So that's kind of interesting. We also asked FPGA users what they're doing. A little over half of FPGA designs have multiple processors. Seems like most of the spike is in the ones that have 2 processors. So more and more software is becoming part of the system. And it's at the point where software is actually implementing the functionality. It's no longer software just setting a bunch of registers and letting the hardware go. Software is actually doing a lot of the work. So we need to be able to bring that into the whole idea of what is a system and how are we going to verify it. So the idea that we want to be able to do with portable stimulus is kind of 2 axes of portability, if you will. One is block to system. The other is platform to platform. So we're going to be talking about that throughout the day. So how you go from simulation to emulation to FPGA prototyping to post-silicon, maybe starting a virtual prototype, whatever. What we're going to go through today is a block to system story. And as we go through that, we're going to talk about how we go from platform to platform as well. So at the block level, we have a block, maybe it's a modem. We have a couple of pieces of VIP on each of the interfaces. So UVM is great for doing constrained random at the block level, right? Because we can control each interface, we can randomize things, we can make sure that we're going to uncover things we hadn't really thought about. And we have what I refer to as external stimulus, which is kind of modeling the real world, and we all know the real world is a messy place. And the other is the internal VIP, which is sort of the rest of the system. SOC level tests, however, are driven more by use cases, not as much by random stimulus and random stuff going on all over the place, at least the way it works today. Embedded software tends to drive the test. They're usually written in C. They tend to be more directed. And this is good and bad, right? So it's good because we kind of know what we want the system to do. It's bad because we don't get a chance to really check and make sure that the system doesn't do anything it's not supposed to do, right? And that's really the value of randomization. We still want to be able to test the block as much as possible as part of the system, so we want to reuse that test intent. But the trick is that we have to coordinate that with other traffic. And we have to do it in a way that's abstract enough that we're not bogged down at the system level trying to say, well, okay, how am I going to actually make sure that the data that went in here came out over here? And it's, right, we have to coordinate stuff with the whole system and have an abstract idea of what does it mean for this thing to work. Right? And so that's what we're really trying to do. I talked about reuse across platforms, right? We want a single specification of our test intent. This is the critical thing. This is why system level verification is so difficult right now, is because we have a group of people doing stuff at the block level a group of different people doing different things at the subsystem and the system level, and we want to try to get them all to work together. So the way we do that is by thinking of the scenario space. So we're going to capture the interactions and the dependencies and the resource contention between all of these things that go on. And the key to that is abstraction, right? I've been doing this a long time, and in a few slides I will tell you exactly how long I've been doing it. But the key to making things go faster and making people more productive is abstraction. This is why we don't design with schematics anymore, right? You have to be able to abstract things. The real thing we want to be able to do is let the tool automate the generation of these tests so we can target these multiple platforms that we want to work on, and we can customize those implementations to a specific target. So we might have multiple flavors of a particular implementation. One might have 4 CPUs, one might have 8, one might have 32 DMA channels, one might have 16, whatever, right? There's lots of different things that can be customized about a given particular implementation, and we want to be able to take that information and work that into the generation of tests for those specific platforms. In that survey, we also asked people what was the biggest verification challenge. At the top it says, creating sufficient tests to verify the design. And this is true of both ASICs and FPGAs. Right? The hardest thing to do is to write enough tests to make things happen. So the value of something like UVM at the block level is you write one piece of code and you rely on randomization of the transactions that get generated to uncover different aspects of your design. What we want to be able to do is to take that idea of one specification, lots of different scenarios, and apply it at the system level. And not only at the system level, but starting at the block level and working our way up. So, how many of you are under 30 years old? Don't be shy. All right, great. The story I'm about to tell you happened before you were born. When I was in college, I went to college in Boston, technically Cambridge, but I lived in Boston, and I co-opted out in Oregon, ironically right down the street from where Mentor Graphics headquarters is. Well, Mentor headquarters now, I guess. So what I wanted to do was to start in Boston and drive out to Oregon. So I said, well, okay, from Boston I can go west, and I'm going to get to Buffalo if I take I-90 all the way to the end. And then I have a choice, right? I can either keep going west and stay in the US, going through Chicago, Salt Lake City, and eventually up to Portland. Or I could go north and go through Canada. Now I have relatives in Canada. I've been there. It's a nice place. Been to Niagara Falls a couple times. Turns out actually the best picture that I ever had with my girlfriend was a picture of my twin brother and my girlfriend. While I was driving around not wanting to pay $30 to park at Niagara Falls, they took the picture. So anyway, Niagara Falls is a nice place. So if I go, but once you go there, you don't want to double back, right? So you want to keep going north and you can go up through Michigan, et cetera, right? So there's lots of ways you can go. The question is, if you're going to program like this, how do you adjust the scenario, right? If I decide instead that I want to go somewhere else, how am I going to change that program? So this is why we have things like constrained random and object-oriented, right? So now what I might have is a class that says I'm going to drive. I have a start point and an end point and a direction. And so when I start my trip, I'm going to start in Boston. I'm going to drive west until I get to Portland. That's not too bad, right? The nice thing about this is I might decide ahead of time that I don't want to go to Canada, so I can just build that right in, and everything's good. So now I can get going. The problem is, as I did this, I decided I wasn't going to drive the entire way myself. I did wind up driving back myself. But on the way out, I had a buddy who lived in Minneapolis. He wanted me to drop him off at home, and then I could go out the rest of the way. So actually, there was another friend of ours who was going with him to Minneapolis. So the three of us drove. It was really kind of weird. My car got just the right amount of gas mileage, had just a big enough tank. So every 4 hours, we had to stop and fill the tank, and we switched drivers. So we made it out 24 hours straight from Boston to Minneapolis. And that was great. So basically what we did was we extended our model, and we added a constraint that said, okay, from Chicago, I want to go north and west until I get to Minneapolis. Then from there, I was on my own. I had time before I had to start my job. And I said, I want to do a little sightseeing. I wanted to go to Mount Rushmore and Devil's Tower. They're pretty close, but aside from doing all this stuff, I also happen to be slightly OCD. I hate backtracking. So I had to know that the Devil's Tower was east of Mount Rushmore. So I had to go there first, and then from there I could go to Mount Rushmore, and then from Mount Rushmore I could go on to Portland. So I had to know those details in order to be able to define the constraints to allow my randomization to get me from Boston to Portland. So I'm still kind of thinking slightly more abstract than saying go from here to here to here, but I do have to be aware of those details. And I had to do that, and back then I had to do it with a paper map. Instead, what I want to be able to do, and this is where Google Maps comes in and things like that, is say, okay, I'm starting from Boston, I want to go to Portland. And it turns out there are lots of ways you can get there. I only chose about 4 of them here, right? But even with this, there's lots of different combinations. And so the question is, do I still want to go to Minneapolis or not? Maybe when I'm coming back, I want to do a different set of things, whatever, right? But I still want to be able to go to Mount Rushmore and the Devil's Tower. So I want to set a few system level constraints that say I want to go here, here, and here. I want to mostly go west. I don't want to backtrack. So now I have declared what it is I want to do, and I let the tool figure out how I'm going to get there. This is declarative programming. This is not procedural programming. You specify your intent and you let the tool do the work. This is what we're trying to do with portable stimulus. So as I said, portable stimulus requires abstraction, so we want to start with the end in mind. Now, we've been thinking about this, as I said, for a long time, and what we realized right up front, and having been at DVCon back since it was HDLCon, back when we had Verilog and VHDL, everybody knows translating from one language to another is really hard. So we did not want to do that, because each target language has its own semantics. There's lots of other idiosyncrasies between languages. We did not want to say, okay, you can start here and we'll figure out how to translate there. Not going to happen. Instead, we wanted to focus on the common semantics at an abstract level. So what we're talking about doing is scheduling between well-defined behaviors and allowing the semantics to explore those scenarios based on the scheduling constraints and the scheduling semantics that we defined. So we're starting with this abstract representation of a stimulus model, and from that generating the different implementations. We're not starting with one and translating into another. We're starting at the top and making different implementations. That allows us to take a single partial specification and expand it into multiple scenarios, and we're going to talk a lot about how we do that. The way this is all going to work is we're going to start with an abstract portable stimulus model, and we'll see a lot about how we model test intent today. From that, there's going to be a PSS processing tool. Again, you're going to allow the tool to do the work, and that tool is going to take that description, compile it, analyze it, do whatever, and build the semantic data model that represents the static structure of the thing that you've defined. And as we'll see, that static structure has a lot of holes in it, a lot of places for the tool to go off and explore different things. So we have to be able to solve those equations. And we can do that in 2 ways. We can do it at what we call gen time. So if you're going to create the test first and have like a piece of C code that you'll then run on your processor, we have to solve all that stuff first before we can generate the code. Or we can generate code that will run in simulation that will at runtime go and talk to the solver to figure out what's the next thing to happen. Right? Different tools do different things. Different applications require different ways of dealing with it. A good tool will be able to do either one of these. And then we're going to take that and have it talk to target platform code that you've written. Right? So if you have driver code already written for your device, what we're going to be able to do is allow you to call those driver functions in interesting ways to make sure that your system is actually going to do what you think it's going to do. More importantly, do what you intend it to do. Right? So this is kind of how the whole thing is going to work. It is important to understand, as we talk today about what portable stimulus is, what portable stimulus is not. Portable stimulus is not a UVM replacement. It may replace pieces of UVM. In fact, we're focusing mostly on stimulus, but there's other parts of it, right? So you may, once portable stimulus becomes mainstream, which hopefully will not take that long, you may never write a UVM sequence again. Or you may actually write UVM sequences for your agents, but never write a virtual sequence that tries to coordinate them again, right? That's what portable stimulus will allow you to do. It is not a UVM replacement. It's certainly not going to replace UVM agents, environments, tests, etc. Right? It's a way of weaving this high-level test intent into an existing UVM infrastructure. It is not a reference implementation. We are not providing a reference implementation. We are defining the language, the semantics, etc. There may be some things that are provided. The standard actually defines a bunch of C++ header files that you'll use. That is not a reference implementation. That is an API spec. It is not one forced level of abstraction. So we're not trying to force you to always think in one certain way. The idea is that you have different perspectives depending on where in the scheme of things you fit. And we want to be able to express that intent from those different perspectives. It is not monolithic. As you'll see, everything here is reusable. You can take a piece of portable stimulus and put it in a different portable stimulus model, all that kind of stuff, right? Everything is composable from parts. It is not two standards. It is PSS. There's what we call DSL, a domain-specific language. It is a declarative language. Existing languages do not let you specify the kinds of things that you want to specify. It is a C++ library that implements the same semantics. So that is also not a language. It's a library of C++ stuff. And Adnan will talk a little bit more about this, I'm sure, that allows you to specify the same kinds of things. So if you're a C++ expert, it doesn't mean you can write portable stimulus unless you know how the portable stimulus C++ library works, right? You have to understand that. And a tool will be able to consume both formats and possibly a mix of the two. That's going to kind of be a tool thing, I think. It is also not just stimulus, right? Is Brian Bailey here? Brian's been after me for years to have not called it portable stimulus. It's really, we're modeling verification intent, right? So stimulus, coverage, scenario level constraints, those kinds of things. And as we said before, it's really portable test realization. So once you figure out what it is you want to be able to do, that ports from platform to platform. So the projected tool flow, you're going to describe either DSL or C++, whatever input flavor you choose. That's your abstract partial specification. We'll talk about what that means. You're going to compile the DSL, or you're going to run your C++ code to create this scenario model and a set of constraints for it that the tool will then use to solve to create your model. So what is it that you've actually intended to specify? And then from that, we're going to generate tests. And we will generate a single test for each possible solution of that set of scenarios. So if you have a model that turns out to have 10,000 different scenarios, we will generate 10,000 individual tests for you. Each one does a certain thing, but when you put them all together, you've effectively randomized the solution space. Every programming language ever starts with a hello world example, so we're going to have one here. So the first thing we're going to talk about is what we call atomic action. So an action is a unit of behavior. Inside of that, we are going to have something we call an exec block. And the exec block is the thing that lets us define how this particular behavior is going to be represented in our target system. And as we'll see, we can swap in and out different execs depending on what the target is, but the behavior is the same. It's going to display hello world. We put it in what we call a component, which allows us to have these things as reusable pieces of stuff that we can put around. And as we'll see, a component in portable stimulus roughly relates to a piece of your target system. We'll see what that means in a minute. When we go and generate code from this, the tool will put together whatever is necessary for the target, such as a UVM sequence, but it will take the guts of that exec block and put it into the resulting code output. So that display hello world shows up as part of the body task in this UVM sequence. And when we do that and we string a bunch of these together and we create a virtual sequence that allows them to coordinate how those things execute, that's how you get a UVM test from a portable stimulus specification. So we have reuse, composition, abstract behaviors, and retargetable implementation, all in 5 lines of code. The next thing we have is compound action. So you want to be able to build up behaviors from other behaviors. So we're going to break that out into 2 different actions, one that says hello, one that says world. They each have their own exec block. And then we're going to create what we call a compound action, which says, okay, I have a hello action and a world action, and I'm going to create an activity which schedules those behaviors so that I say hello world and not world hello. And when I go and generate the code, and in this case I generate C code, I'm going to print hello, and then I'm going to print world. So now we have behavior encapsulation and behavioral scheduling in another 5 lines of code. Then we have data flow objects. So I may have a generic action that says display, and I'm going to create a thing that we call a buffer. So this is what's going to define data flow. So this is a piece of data that flows from here to there. And we also have things called stream and state, and they each have their own semantics. So a buffer is, as you might expect, a buffer is something you can create, throw it over there, and sometime later somebody else is going to pick it up and use it. Inside the buffer, we can have random things. Just because we're dealing with strings, I have a random string in here, which obviously doesn't make a whole lot of sense. We're going to constrain it later. But we can have random numbers, random enums, whatever, as part of the buffer. So when we create a buffer, we're going to randomize the things that are random in it. And there are other things that may not be random, right? So we can randomize data as we need. And then we define for this display action, it has an input of this buffer type. So it is going to take as an input a string, and its implementation is going to take the string field of that buffer and print it out. And we use this double brace thing we call a mustache. You can spell it either with or without the U. So that's how we do it. We can take pieces of the portable stimulus model and pass them down into the generated code. So we have complex data structures, we have data flow modeling, we have constrained random data, and we have reactivity, all in another, we'll call it 8 lines of code. Then what do we do with these data flow objects? Well, we're going to create now a send action, which is going to send a message out. Now our compound action hello world is going to have 2 sends and 2 display actions. And we'll put in an activity, we're going to say send 1, display, send 2, display. These lines here represent control flow. So I'm going to execute my actions in this order, and the brown stuff is the data. So I can bind the output of send 1 to the input of display 1, and similarly I can bind send 2 to display 2. So this says the data that I generate out of send 1 is going to be displayed, etc. Right? So this is how we're going to do it. And now we can add constraints in. So I can say, okay, I'm going to send a hello from the first one, which means it's going to be displayed by display 1, and I'm going to send a world with the second one, and it's going to be displayed by the second display. So what I have here is a directed test. Tightly constrained, only one possible solution. This is what I have. And if this is what you want to do, this is fine. You can do it. What I may actually do instead, as a general modeling style, is instead of constraining the thing that gets sent, I can constrain the thing that gets displayed. It's the same data flow object that's being constrained from either end. The constraints still have to match. So when I constrain the input, that effectively it's constraining the thing that created it as the output. So now I have the same thing. And now what I have is I have directed testing when I want to, and I have inline constraints if I need them. So I can specify for a given test, I can add constraints in when I want them to. I can also add constraints as part of the data itself, and we'll see that in a minute. But I can also take that definition of the buffer and put it in a package. And then I can import the package in my component, and now I have everything that I put in that package available to me in the component. Everything else in the test stays the same. So we have additional reuse and encapsulation through the use of packages. Now, here's where portable stimulus gets really cool. And this is its ability to infer behaviors based on what you tell it. So instead of having this fully defined test, what I've done instead, you'll notice I got rid of those 2 bind statements. So now I have a send and a display, etc. I don't even actually have to say send, because each display has to have something to display, so there has to have been something that created it in the first place. So I don't have to specify those 2 send actions, because I know they have to be there. The tool will figure that out and put them in for me, and I have the constraints, so I know how those things that I'm going to infer are going to be constrained. So now I have less code. I've specified what it is that I want to have happen, because what I really care about is that I'm going to display hello world. I really don't care where the data came from. So having that message that I'm going to display, I know it's going to come from send, so I'm implicitly doing a send, then a display, and a send, then a display. So this is an abstract partial specification. But that's not really the only thing that we can do here, right? So I have my 2 displays. I could, in my activity, insert a select statement. So it says, I'm going to randomly pick one of these 2 branches. I'm going to display either hello or world, not both. So when I generate this, there are 2 possibilities for my solution space. So when I run the tool, I will generate 2 different implementations. One's going to say hello, one's going to say world. So in effect, what I'm doing is picking between these 2 branches, and I can do that. So now we have scenario level randomization, right? I'm picking one or the other. Each test is only going to do one, but when I put them together, I do every combination. In an activity, there's lots of things that we can do. So by default, they happen sequentially, so I can specify an action. We call it action traversal. It's not really execution, because in the portable stimulus model, we're not actually executing it yet. We don't execute it until we actually generate it and run. But we traverse the action, and that implies that we're going to randomize all the pieces of it and do whatever, right? We can also specify an anonymous traversal, so I don't have to instantiate something and then traverse it. I can just say do whatever. We can run things in parallel. We can run things in sequence. We can select, as I said. This is really powerful. This is called schedules. From the set of things that are in that block, I will execute them in some order based on whatever other constraints are present. So I might do A followed by B. I might do B followed by A. I might do them in parallel. I might have strings of 4 or 5 or whatever. I can do them in any order based on other constraints that we'll talk about. I can do if-else. So I can do an if that something happened in the system, right? I can have data reactivity and make decisions. I can repeat. Now I've shown it here. It looks like I've unrolled the loop. We don't actually do that. It's just a way of making it easier to draw. And we also have for each. So for each element of an array, we can do certain behavior, right? From that, you can do an awful lot of stuff. You can specify some really complex things. And the beauty of it, though, is that you don't have to specify all the complex things. You specify what you really, really want to have happen in the activity, and then all the other stuff is basically rules for the tool to figure out what does it need to do to support that critical activity. So we have robust scheduling support as well. We also have extension and inheritance. So we can say, okay, I'm going to extend my component, and I'm going to add in there a definition of a new buffer, and this buffer inherits from the message buff type. I'm going to call it hello buff, and I'm going to add my constraint there. So I can build my constraints directly into the data flow objects if I want. I can also build them into actions as well. And then inside my action here, which is my display hello, I'm going to inherit from display action and override it. So I'm going to say that the type of message buff that I had specified before is now a hello buff. So display hello can only use a hello buff as its input. And then I have an action hello, which is going to output a hello buff. So I have type extension, object-oriented inheritance, and type and instance override available as well. Now I've constrained my hello buff. I'm now going to say it's either in English or in German, just because. So now I have to be able to specify what I'm going to do with these things. So we create what's called a pool of hello buffs, and we call it LOP. So this is a group of data objects that I'm going to tell the tool what is it okay to do with these things. So what I'm going to do is I'm going to bind that pool of hello objects to anybody that will have it. So I can use the wildcard. I can be more specific if I want, and we'll see examples of that as we go. And I can also create a pool of world objects that are constrained to be world in either English or German. So I can constrain my data paths, and I can preserve my intent in that way, because now I know that I have certain things that are constrained in certain ways, and those objects can only go to the set of actions that are expecting them. So now what I can do is I can say I'm going to do a sequence of display hello followed by display world. Right? This is my hello world example. So I'm doing display hello, display world. Therefore, I have to infer that I'm going to send the hello and the world in the first place. So this might be one scenario that I could infer. Right? So I have my anonymous action traversal here. So in the first case, I'm going to do it in English. Then I might actually do hello in German, but world in English, and vice versa. So there's essentially 4 different paths through this particular scenario, given the set of constraints that I have. But I have a little more flexibility. The only thing I've specified is that I want to do hello first and world second. There's nothing that says that I can't do both sends first and then both displays, because as we said, the buffer thing gets sent over here and then picked up later. So as long as the display hello and display world happen in order, I don't care what else happens. In fact, those 2 sends could happen in parallel if I want, as long as the data exists when it's time to do display hello and display world in order. That's all I care about. So I have all of these different scenarios from a single 2-line specification of my intent. And obviously this is a pretty simple system, but you can imagine the power of this sort of thing when you specify, I want these critical behaviors to occur in my activity, and I've defined the data flow objects and all the other rules around it to allow the tool to figure out all these really cool scenarios. So we have multiple scenarios from a simple specification. We can also do this in C++, by the way. All the code that we just showed has a C++ counterpart to it. So we have a package, we have a buffer that we can specify, so there's a constructor in there. And then there's this type decal thing, which is basically a way of telling the tool that this thing exists as defined in C++, even though I didn't necessarily instantiate it in my model. Right? We have to be able to do that. Then we can also specify a component, which again has a constructor. We can specify actions, which has an input. We can define the exec block. And the same for the send action. We have outputs, etc. So all of the things that exist in the DSL have a one-to-one corollary in the C++. And the same for pools and binds and the way that you, right? And we have activities, and we have the ability to select or do whatever. All the things that you can do in an activity in DSL, you can do in an activity in C++. And again, we have the type decal down there to tell the tool that these things are there, even though I haven't necessarily instantiated them, right? So this is why I said before, when you take the C++, this is not the C++ that's going to execute your code on your target. This is the code that's going to define the model that you're going to use to generate the code that's going to execute on your target. So just through this very simple hello world example, PSS gives you all of this. And these are all really good things, if I do say so myself. But wait, there's more. So now we're going to take you through a block to system example. So we have our block here, we have our modem, and again, we have the real world, the external stuff on one end, and the internal stuff, the rest of the system on the other. So we're going to go through how we're going to do this, how we're going to set this up, and then we're going to show you how you take that and reuse it in a subsystem. Right? And a subsystem is a bunch of stuff with a CPU, but not everything. That's sort of the definition of a subsystem. Right? Without the CPU, it's just a bunch of block level stuff, and we kind of know how to do that. And once you throw the CPU in it, you have software as part of the system, and you have to be able to figure that out and define how that's all going to work. And then we have the system level model, which is everything. So the only difference between a subsystem and system is how much crap you have thrown in the 5-pound bag, right? So for the block level, we're going to define what are the actions that we have to have these things do. So what does the modem do? Well, it receives packets and it transmits packets, right? It's pretty much all the modem does. So what data flow objects does it use? Well, on the external interface, it has a packet. What's a packet? Packet is whatever you want it to be. And on the inside, it has a data stream object. And we'll see in a minute why I'm specifically calling it a data stream. Through several iterations of this tutorial, it has been called several things, all of them perfectly fine. And now we call it a data stream because it's important that we understand that this thing is a data stream because there's no storage, at least as we've defined it, in the modem, right? When the data comes in, it has to go out somewhere, and somebody better be ready to catch it. Otherwise, it's going to drop all over the floor, and that's not going to be good. So what does the external IP do? Right? It's modeling the real world. As far as this thing is concerned, all the real world does is it sends packets in and gets packets out. It might do other things, but we're not going to go there. Right? There might be interrupts, do whatever. All we're worried about for the purposes of this tutorial is it's going to send packets in and get packets out. And what does the internal IP do? Well, the internal IP is the rest of the system. So that means that when the data stream comes in, it's got to do something with it. And when I want to send data out, the data's got to come from somewhere, so it's got to send it. Right? So we store data streams and we retrieve data streams on the internal IP. As far as the modem is concerned, that's all the system is doing anyway. So we have to model it. All right, so we look at the data flow object. So we have, in our data flow package, we're going to define an enum. So we have enums. And we're going to use that to define the direction. So it's either inbound or outbound. So we can define enums. We can, just like System Verilog, we can define explicit values for things in the enum, or it'll just automatically increment them as we go. So inbound is 0, outbound is 1. We can define a stream. So before we had the buffer with the message, now we have a stream that's the data stream. The only difference is that the stream defines that the producer and the consumer have to execute in parallel. There's no storage of a stream object. Some action has to be there ready to catch it. But just like the buffer, it can have randomized data fields in it. They can be constrained. You can specify them however you want. So the stream and the buffer are essentially types of data structures. So we do actually have a default data structure type, a structure, and you can inherit either buffers or streams from the structure type to be either a buffer or a stream, and each buffer or stream can also inherit from an existing buffer or stream as well. So in some examples that we've been working on, there's a base data type, and we extend that to be either a stream or a buffer, depending on what the requirements are for that particular piece of data. We can randomize the fields of the data object, and we can also have a packet stream as well. Now what we have is we have our component, which is the LTE modem component. So this is a piece of our portable stimulus model that corresponds to the block that we're actually verifying. Right? It is not a model of the block. It is a model of the stuff that we intend to verify about the block. So in a lot of cases, there's going to be a one-to-one correlation between a component in the portable stimulus model and a piece of your design. But we are not designing in portable stimulus. We are specifying the intent of how we want to verify the thing that we've designed. Okay, very important. It's easy to get confused. You decided to call it a component because it represents that piece of stuff that you're actually verifying, and it's a reusable thing in portable stimulus. It actually kind of serves as a namespace as well, for those of you that care. So we can import the data flow package into this thing, and we define our actions. We have a receive action. So we're going to input a packet, output a data stream. We're going to specify a constraint that says that these things are inbound. I drew the data flow from top to bottom here, but at least I did not violate a cardinal rule of design that was drilled into my head back when I was in college, which was the teacher said, the easiest way to confuse an engineer is to have an input coming in from the right. So at least I'm having them come in from the top and the bottom. All right, so things are inbound. So I have an exec body here. Now, inside the exec body, I'm going to call this thing called set mode, and I'm going to pass it in the direction. So what is set mode? Well, set mode is a function, or a task in system Verilog actually, but as far as portable stimulus is concerned, it's a function. I'm going to import this thing, and it says set mode is something that is defined through what we call the procedural interface. So it's in whatever target language you want, right? You can have a system Verilog set mode, you can have a C set mode, you can have a Python set mode, whatever, right? As long as it takes a direction as its input, and that is going to be the code that is going to get called for this exec block. And so for your tool, you say, okay, this is the thing, and by the way, I'm importing functions from this piece of code, system Verilog or C or whatever, right? So you can, that's a tool issue. As far as the model is concerned, there's this thing that's going to set the mode, which will do whatever is required to that modem to set it up to get data in the given direction. So setting registers, doing whatever, right? So that's what has to happen, right? So it's a procedural interface, and it can pass in information from the model into the exec block. And we can do the same thing on the transmit side. The only difference is now we're outbound. The VIP components themselves also have behaviors associated with them. So in the external VIP, we have send and receive. Notice send only has an output that is inbound, and receive only has an input that is outbound, because we don't care what's going to happen to those things on the other side of it. So we only specify what we care about as far as the intent of verifying the modem block. Right? And similarly, the internal VIP is the same thing kind of in reverse. So the store data takes a stream as an input and is inbound, and the retrieve outputs a data stream in the outbound direction. Given that, we can put this system together, system in quotes, right? It's a little block level environment, right? So in my component, my top level component, I'm going to import my data flow package. I'm going to instantiate my three components. I have my external VIP, my modem, and my internal VIP. And each of those has a set of actions associated with it. I'm going to create my packet pool, and I'm going to bind that to the external VIP and the modem. And I'm going to have my data stream pool, and I'm going to bind that to my modem and my internal VIP. Then I'm going to say, schedule, do a transmit and a receive. So that means I can do those in any order. Right? I can do receive first, then transmit. I can do transmit, then receive. I can do them in parallel if I want to, if I can, right? If the system will let me. And we'll see what that means in a minute. Okay, now, why did I go to the trouble of specifying the inbound and outbound thing? That's because, as far as my intent is concerned, this path is illegal, right? I can't take the data from the receive action of the modem and send it directly to the transmit. When the data comes in receive, the only thing it can go to is another action that's bound to the same pool that is constrained in the same way. Right? And similarly, if I'm going to do a retrieve, I don't want the retrieve to link back into the store. Okay? So that's why I have that inbound there, is to allow the constraint of the data objects to define what makes a valid scenario when I start pulling these things out of thin air and sticking them together. Right? I have rules about what is legal and what is not. So when I put it all together, now I have my schedule of things going on. So here's what can happen, right? What I've specified is I want to do a receive and a transmit. That's the critical intent of what I want to have happen. But in order to make that happen, there's other things that have to go on in the system, such as doing a send to generate the data in the first place for the receive, and a store to take the data out the other side and do something with it. Similarly, for the transmit, I have to retrieve the data, send it to the modem, and something else has to catch it on the other side. Those things have to happen for the test to be successful. And the rules that I've defined tell the tool that those things have to happen. So all I've told the tool really is that I want to do a receive and a transmit. It knows it has to then pull all this other stuff together based on the rules I've specified to create the actual scenario that's going to execute. I can also do transmit followed by receive, or as I said, I can do them in parallel as well. So 2 lines of code, 3 different scenarios with 3, 6, 9, 12, whatever, right? A whole bunch of actions going on, and all assembled in the right way based on the rules that you specified. So it's really important to understand. So we've got the activity here, which defines the critical intent, the stuff that has to happen. This is the stuff that I really want to verify. And then we have all the rules that allow the tool to figure out how to support that and make it legal. Now, what if my modem is only half duplex? I can't do a receive and a transmit in parallel. How do I tell the tool that? Well, PSS allows us to model target-specific resources, right? What are things in the system that I have to play with? And we can define them as either exclusive resources, so they can be locked, or they're non-exclusive, they can be shared. In this case, we're going to say, well, okay, the modem itself is a resource. I've only got one. It can either receive or transmit, but not both at the same time. So I'm going to create in here a resource called modem channel, right? So there's a channel that goes in there. So this is the resource object. So I'm going to create a pool of resource objects, right? So every object is in a pool, whether it's a data object or a resource object, it's in a pool. I can specify how many of these things exist. The default is 1. In this case, I've made it explicitly 1 just so you can see the syntax. But I could say maybe there's 4 modem channels or whatever, right? So in this case, there's only 1. That means that I can only do one operation on the modem at a time. And I'm going to bind that to anybody that's looking for the resource. So in the receive action, I'm going to lock that channel. And a lock says that that's the only thing that can happen at that time. So actions can lock or share resources. So what does that mean? Well, I'm going to define a resource here. So I have a resource that's called channel, whatever that means. And I have a pool that has 2 of these things in it. And I'm going to bind that channel pool to anybody that cares. Right? That's what the asterisk means. Now, I have a locking action that's going to lock that channel. And I have a share action that's going to share that channel. Okay, so what does that mean? Well, any 2 actions that lock a given resource cannot overlap. They have to operate sequentially. Okay, that's just the rule. So if I do rlock1 and rlock2, they have to happen sequentially. I can have 2 actions that lock a resource happen concurrently, but they have to be locking different resources. So each resource has built into it a field called instance ID, which is unique for the given pool. Okay, so in this case, I have 2 channels. One is ID 0, one is ID 1. And so by definition, by executing the 2 lock actions sequentially, I am constraining the resource IDs of those 2 resource instances to be different. So the resource ID of the thing that's used by rlock2 is different from the instance ID of the resource that is used by rlock3. What that means is, since there's only 2 of them, I can't have a 3rd locking action happen in parallel. It just won't work. For sharing, options that share a resource can overlap. They will also be randomly assigned a resource. If you want to, you can actually constrain the instance ID of the resource in the action. By default, we'll just pick a random one for you. And there's no guarantee what the relationship is between them. So in this particular case, these 3 shared actions can all be using the same resource instance, or 2 of them could be using one and one could be using the other. Because the 2 locking actions are taking up all of the resources available, there isn't another resource to share even, so up there I can't do anything else once I've locked both of those resources. But in the share case, as I said before, since all 3 of those could actually be using the same resource instance, there could be one left over for a locking action to use. So in this particular case, what that means is that those 3 have to use the same one. The instance ID has to be the same. And that instance ID will be different from the instance ID of the one that's locked. And again, because we have constraint sharing, if one of these share actions specifies the instance ID specifically, the other 2 are implicitly constrained to use that same instance ID. It just kind of makes sense. Okay, so that's really what we have here. So again, there's a set of rules that you can use to define how can I customize my scenario based on the set of stuff that I have available in my system. So a total of size locking actions can execute in parallel for a given resource pool. And then you have the shares that you can fit in as necessary. Okay, so this is now pretty much everything you need to know about how you're going to specify what it is that you intend to verify and what are the rules that are necessary to create actual implementations on your target platform to verify your design based on its configuration, its resources, the other pieces of IP that you have available and the things that they can do as well, and what the data flow is between all of them. Once you have all this, this is what the tool is for. But I want to explain to you guys how the tool is actually going to work. Because what I've found in my many years of doing this is tools are great. But once an engineer loses sight of what the tool is going to do, he may as well be one of a million monkeys trying to write Shakespeare, right? I was actually working as an AE once, a long time ago, for a company. We had a graphical tool. You could enter state charts and stuff, and we would generate Verilog or VHDL for you. And at the end of the project, it was my job to run the design review for our customer. And so everybody would come in with their pages and pages of state charts, and I would sit down and go through them with them and see if they did a good job. And the one question that I would ask is, okay, given the state chart, what's the hardware going to look like? And if they could tell me what the hardware was going to look like, I knew the design was fine. If they couldn't, I knew they were in trouble, right? So as long as you can understand the kinds of things that are going to happen, I don't expect you to be able to necessarily predict all of the 10,000 scenarios that are going to occur. But I want you to understand what the tool is going to do with the information you give it to be able to know what's reasonable and what's not, right? So we start with a pretty straightforward model. So I have a bunch of actions here, A, B, C, D, E, and F. And in my activity, I'm going to do A, then I'm going to do B, and then I'm going to select, I'm going to do either C and D in parallel or E followed by F, right? So that's what this says. So that's my critical intent. That is pretty much a directed random test, right? Because we're going to pick either one of those two branches, but I've pretty much told it a lot of the things that can happen. If instead I want to back off a bit and say all I really care about is I want to do B, and then I either want to do C or F. So again, that's the critical intent, but I have a set of rules that I can use to figure out how I can actually make this work. So maybe I have a buffer called mbuff, and my do A action outputs the buffer, and my do B action inputs the buffer. So therefore, I know that I have to infer an A to feed B. But I might have another action G that outputs the same type of buffer. So I could pick a G in there instead. And then I might have a stream, and C inputs the stream, and D outputs the stream. Technically, the input's going in from the right. Sorry about that. But I might also have a J that outputs the same stream type. So what does this mean? It means that from this given specification in here, B followed by C or F, I can infer a bunch of different scenarios. And it goes further than that. Just because A produces the kind of object that B requires, B also happens to output a buffer. So I can actually go A to a B to another B, and then go from there. So there's nothing that says that there's a limit that you can only pick one thing to drive it. If that also has other requirements, you have to go fill those in as well. So the partial specification is extraordinarily flexible, and the tool has to go through, right? I said before, you start at the top, you compile the model, you figure out what it is that you have. And I said that that model has a lot of holes in it. And then you got to figure out how you're going to fill in the holes. Well, this is what I meant. So this is my partial specification, right? I have B followed by either C or F. So B has a buffer input, it produces a buffer output. F has a buffer input, and C has a stream input. We're not going to worry about that for now. So let's worry about how we're going to supply the buffer to B. Right? We have a whole pile of stuff over here, and these are actions that are either defined in DSL or they're in C++ is what the type decal is for. I haven't necessarily instantiated them, but the tool knows they're there. So now I have this pile of stuff, and I got to figure out what do I need to take from that pile to go and put it into my design to make that happen. So I have this big hole above B. What do I put in that hole so that I'm going to eventually create a buffer that B requires? And because it's a buffer, that means that whatever behavior I specify up here has to happen before B happens. Those are the rules. So I can pick an A, right? A generates the right buffer type, executes before B. That's a valid solution. I could also do a B, because B also produces a buffer. But then that B has to be fed from somebody. So that B can be fed by an A. I also have an E. Right? E produces the right kind of buffer on the output, but E has a stream input. So now I got to feed that stream input. Okay, well, who has a stream output? Well, D has a stream output. So I can put a D in there, but D has a buffer input. So now I got to figure out who's going to supply the buffer input. It could be an A. It could also be a G. So I can do that as well. Now, since A and G don't have any inputs, if I pick one of those, I'm done. But it could also be a B, and then that B needs something to feed it. And it could be an A, it could be a G, it could be another B, right? So there is a limit to how far you can go, right? And that's a tool-specific limit. Figure it'll be somewhere around 128 or whatever, right? Or 1024, whatever, right? However bizarre you want to allow the tool to be, you can let it do that. So, and every time we pull in, we might infer an E, then that implies that it also has something that has to be fed, and then we got to figure out how we're going to feed that, right? So we have to build up everything that's necessary to create a valid scenario, remember, whose goal is to simply fill in this hole and provide a buffer to B. Whatever is required for that, that's what we're going to do. B has a buffer output, F has a buffer input. So we got to figure out who's going to supply the buffer input to F. As I said before, it doesn't have to be B. So what's going to happen in there? I'm not going to go through all of the graphics to make that happen there, but it's the same sort of thing, right? The interesting thing about a buffer is that a buffer doesn't necessarily have to be used by anybody. So F's ability to require a buffer means that we got to have somebody supply the buffer, but it is possible that the buffer that B generates can just be ignored. We said we're still looking at enhancements. One of the things we might do is define, well, okay, B has an output, and I really want to make sure that somebody uses it, so we'll add that in. Right, so we have this hole in here that we got to fill in. We also have the stream object for C, so we got to figure out what's going to happen. So anybody that supplies that stream object to C has to execute in parallel with C, and those things are going to happen after B because of the way we've defined the activity. So the only requirement here, though, is that C happens after B. But if the thing that feeds this stream has its own buffer input, and we take this whole set of stuff and infer a bunch of actions up there, that relationship is independent of B, unless there are other requirements, right? If one of the things that I infer locks the same resource that B happens to use, I can't infer that to execute in parallel with B. So again, as complex as this might be, coming up the left-hand side of the graph, I still know what requirements there are as to how those are going to interact with the other things that I've already specified or inferred to support B. So as I pull all these things together, I have certain things that are definitely required that I've specified in my activity, and I have certain relationships between things that I might pick out based on resource contention and other things, and so I can figure out how they can relate, and I can pull them all together, one big set of solutions, and then from there I can generate my implementations. And again, there's also the space in between B and C there that might cause other things to happen. So there's a lot of flexibility in there, but the important thing is that the stuff that you care about is the stuff that you've explicitly put in your activity. Those are the things that you know are going to happen. And now when we think about the UVM case, where you have a transaction that you've specified with some constraints on it, and maybe you have a couple of sequences that are executing in parallel, and they're randomizing transactions, so they're going to cause interesting things to happen on the bus when those two transaction flows intersect. We've taken that a step higher, and what we've specified is not just the constraints on the data that are going to get generated, but the constraints on how those behaviors are going to interact at all. Right? And we can specify, I definitely want to make sure that these two behaviors happen together, and everything else can happen, based on the rules that I've specified to make sure that all of these weird things that might occur are still legal given the constraints of my system. And the only way that you can do that is by specifying these things declaratively. I want to go from Boston to Portland. So I have a certain number of roads that I want to stay on the interstate. If I don't say I want to stay on the interstate, there is an infinite number of ways to get from Boston to Portland. It could take you a couple of months to do it. You might spend half your time sitting in a red light somewhere, but you could do it. But who wants to do that? If I want to really stress the brakes of my car as I'm testing it going from Boston to Portland, I might want to stop at a lot of red lights. So I say, okay, let's stay off the interstate. And the tool will figure out all of these different ways to go, right? You might say, I don't want to go any further south than Missouri, right? So however you want to define it, that will bound the tool to generate the set of scenarios that you want to have happen that will make sure that you're verifying the things that you intend to verify. And you can only do that by taking a step back and defining at this high level what it is that you want to have happen. And because we knew that trying to define Esperanto to allow every platform to execute the exact same code was not going to work, we gave you the ability to say, for this behavior, for the target that I'm shooting for, this is how you implement that behavior. And we give you the flexibility to say, okay, now I'm going to a different platform, swap in this implementation of that behavior. But the semantics of how those two behaviors relate to each other is defined and allows the tool to stitch those things together to implement the intent that you have on the platform that you're targeting. And that's how portable stimulus works.
My name is Adnan Hamid. I'm CEO and founder at Record Verification Systems. Many of you know we've been in the portable stimulus business for a decade or so. Tom left us with, he taught us first a Hello World example with some A, B's, and C's, and then he got us into a modem block test. And then from there, I'm picking up, and we're going to be talking about, Tom already talked about a unit bench. I'm going to start talking about a subsystem bench, and then I'm going to take it to a full system design. So let me invite you to think about three problems as I talk about portable stimulus. One is, UVM is a beautiful thing, right? It'll give us wonderful test benches. But then we end up writing big libraries of sequences. So one thing I want you to think about as we talk is, how can we randomize the sequences you're generating for UVM? Could tools do this for you instead of having to write those by hand, right? UVM brings us great transactional randomization, but when you've got to do these transactions in different orders, it's tough. A second thing I want you to think about is concurrency and resource management, right? When we have subsystems, we have multiple scenarios running in parallel. When we have single IPs, they can have multiple channels that are running in parallel. One problem is getting them all to run concurrently. Maybe that's just a fork. But then we've got to worry about scheduling considerations, right? Maybe there are only so many resources to go around. They need different memory addresses. Maybe certain things need to run at the same time because of streaming relationships. And the third thing I want you to think about is we're running the same tests on different platforms, right? First we go to the IP bench, then we go to the subsystem bench, then we go to the full chip bench. And can we get the same model to generate tests for all of them for us? Okay, so let's talk about this subsystem. Okay, what we're going to take is take the LTE modem that Tom introduced us to and add into the system a second modem, right? A CDMA modem. And the audio codec. So the audio codec is a thing that is a speaker in the microphone that you actually talk to. So we're going to deal with managing voice calls, where the voice calls can either come across the LTE modem that we already looked at, or a CDMA modem, so there's some choice. And both of them stream data to the audio codec. So what's this thing about streaming that we're trying to emphasize, right? We're trying to make the point that certain IPs, like a modem, or a UART even, they need to run concurrently with other IPs that are pulling out their data. You don't just get to generate data and then do something after that. So that's the importance of stream. Let's talk about exec blocks for a second. Tom introduced the exec body to you already. Exec blocks are actually the bottom of the portable stimulus model. This is the guy who actually generates the operations that your test bench can talk to. So there are multiple kinds of exec blocks that we have. One is a header exec block. So this is a thing that will be used to generate any pound includes or anything else that needs to go at the top of a pre-generated test. Then we have declaration exec blocks. This is a way to include code that maybe some function you need to define at the top of the test. Let's say we're pre-generating a test. So maybe there's some test main that's automatically generated by a tool. In there, at the beginning of the test, we may well need to do some initialization stuff that happens only once. So that's our run start exec block. At that point, from the tool's perspective, it's managing multiple concurrent threads, however it generates threads for that. And for each step in a thread, we have a pre-solve exec block and a post-solve exec block. So pre-solve runs before we do randomization, post-solve runs after we do randomization. And then body actually does the operation that we want to call on our test bench, maybe a UVM sequence. And then finally, there's a run end. That is your place to put cleanup code. Now, on my slide, I show a C test, but this may well be a UVM test. It may be any language you want it to be, right? It's whatever language your test bench needs. The point is we have the structure for understanding what needs to happen at the beginning and the end, and then what has to happen at each step in a test. And then finally, we have one more exec block type that's called a file exec block. And this gives us an opportunity to have the portable stimulus model kick out a secondary file, right? Maybe a shell script or a make file or some other batch file that you use maybe for your execution system or so on, right? So multiple ways of generating outputs. So Tom already talked about the LTE modem. I'll talk about the CDMA modem, and I'm going to use this as an opportunity to talk about pre-solve and post-solve exec blocks. So very similar to how things work in System Verilog. I think we call it pre-randomize and post-randomize over there. So the receive operation on the CDMA block, it takes in a packet, it puts out a stream, and has a constraint on the direction and of both. We're importing some functions that know how to set up the source and destination addresses for this CDMA. Okay, here are the important parts, right? So the packet is marked as a stream. That's what tells the tool that when one item is outputting a packet, another action that's trying to input that packet must run at the same time. And then for our purposes, what's important over here, it has these two addresses, right? A source address and a destination address, and they're not random variables. They're not marked as random. Because they're not marked as random, we can set them in a pre-solve routine prior to the tool actually randomizing the variables. That is different than a stream object, which says that the address over there is randomized. So when the tool is solving, it'll pick a random number for it. So if we want to override that random number, we have to do it in a post-solve routine. So that was our CDMA modem. Now let's talk about our audio codec. There's not much new that you're going to see over here. We have an action to do a play. So this is going to be receiving packets from the modem and playing them to the speaker of your headphone. The play function and the record function, these are the things that we're actually going to call to invoke the speaker to play or the microphone to record. And the exec body, now when we actually do an action, right, when we do the play action and we decide it's time to activate it, we're going to call this play function. So right here. When we execute play action, we're going to execute the play function. Similarly, when we execute the record action, we're going to call the record function. And we are putting some constraint on the packet saying we assume that every recording is 1024 bytes. So now let's talk about connecting this all together, right? So I have these two modems. I have this one audio codec. I have a choice of which modem to go to. I can do receive and transmits. So how do we tie all this together? We instantiate the two VIPs, one for CDMA, one for LTE. In this model, we're assuming we can use instances of the same VIP to drive both. So that's our LTE VIP. That's our CDMA VIP. Now we instantiate the component that represents the LTE modem itself, so it knows how to do a receive and a transmit. Then we instantiate the CDMA modem, different component, different protocols, but it also knows how to do receive and transmit. And what's important over here is they have the same API, right, and the same interface. They both want to receive these packets and send out these data streams. And then we instantiate the audio codec that wants to take a data stream as input. Okay, now we construct a pool. A pool is a container, right? So we're going to create two buckets of packets, one called LTEP and one called CDMAP. Why are we doing this? To let us do two separate bindings. We take the pool of LTE packets and bind the LTE's VIP to the LTE component, and similarly bind the CDMA's packets to the CDMA component. So what this lets us do is have two buckets of these packets, and we are implicitly telling the tool that data for the LTE component can only come from the LTE VIP, and packet output from the LTE component can only go to the LTE VIP, and the same for the CDMA. So a lot of words, but basically lets us connect the appropriate VIP to the appropriate component, right? Nothing much more. Then we're creating a pool of these data stream objects. And we're saying, hey, please connect that pool of data stream objects to the LTE modem, the CDMA modem, and the audio codec. So now the tool knows that inputs to the audio codec can come from either modem, and outputs from the audio codec, things that have been recorded, can go to either modem. So just wiring it all up. Then a little bit of interesting things going on over here. So the top level test, this test guy is our entry point for our little simple test. We're going to say we're going to have some activity. And we plan to schedule, as in do at the same time, however the tool sees fit to schedule, two things. We're going to do an audio codec play operation. So that says we want to invoke one of these. And that's simple enough, right? He in turn can say, okay, I need some producer, and it can be the LT component or the CDMA component, and if it's CDMA, his input must come from the CDMA VIP and so on. The thing I want you to draw attention to, the next line is slightly more interesting. He says, and then do a receive operation on a VIP. But both the VIPs have the same type. So the tool is free to pick either one of those. Any instance of that type, he can go pick. So we had one instance that was for the LTE and one instance that was for the CDMA. And the tool can randomize between them and say, okay, I want to do a receive on the VIP from either of those protocols, and that in turn will cause them to get to the right modem and then pull something from the audio to get that going. So this allows you to do what I think of as a randomization by type, right? You can say, give me something of this type, and the tool will go find some instance of that type. So now, when we start thinking about what scenarios the tool could go create, we said, please do an audio play with some kind of a receive. So maybe he will do audio play coming from the LTE VIP, and LTE receive also coming from LTE VIP, for example. Or you could choose to do these two things in parallel, or other combinations of these tests, as Tom talked about before. So again, the main thing over here is we're trying to do longer sequences of operations now with some randomization, right? We have two modems, we have this audio codec, there are multiple ways to go through them. Instead of having to handwrite the sequences of all combinations, right? Those receive and transmit cross by, say, across with CDMA or LTE. We get to build each of the components, let the tool stitch our sequences together randomly. Okay, next thing I want to talk to you about is layering in power management and the state flow object. So this stuff is a little subtle. There's something very cool going on, but you got to catch it. So our intention is now to model power management for a modem subsystem. And we're going to pretend that there's only one radio domain for both CDMA and LTE. And for either receive or transmit operation to happen on either modem, we got to turn the radios on. If there's nothing going on, we can turn the radios off. And we're going to do this layered in. So we're going to define some power state package, that's fine. We have a radio on, radio off function. You've already seen that. There's nothing new going on over there. We have a little enum that's keeping track of whether this radio subsystem is on or off. Nothing new there. We're going to introduce a state flow object, right? So this radio state is a state object, as opposed to what you've seen so far. You've seen a buffer and you've seen a stream. Okay. So state objects are interesting in that they remember their previous states. Okay. Buffers and streams do not. This is the only way to have persistent state in the portable stimulus model. A state object may have an initial constraint. So the variable is true when the thing is starting up. So it lets you set the initial state of this radio to being off. And then we're going to create some top-level component, and we're going to bind this state object to anybody who wants to talk to it. So I'm going to show you where those things get used. So important thing over here is a state object. Think of it as an object that's remembering the current state of the radio, and when it got instantiated, it got set to off. Right? System knows it's off. Now, carrying on with the model, we're going to extend the LTE receive operation to say, hey, in addition to everything else you do, you're going to take as input this radio state object. Okay? And then you're going to have a constraint that says you need that input state to be on. Right? Remember, it started out as off. You need it to be on. Same thing for the CDMA RX, and then the same thing for the two transmit operations. Right? So we told the four actions, hey, when you guys run, you have to demand that the radio state is on. That's all we said, not how to turn it on. Now's the subtlety, right? We're going to define a new action, a radio on action. And he produces as output one of these radio state objects. Okay? And he has a constraint that says he can only run if the previous state of the radio state object was off. Right? So if it's already off, then he's allowed to run and do something. Otherwise, he cannot. So when we're coming into this, the radio state was off, he can run, but if the radio state was set to on, he can no longer be invoked. And then he has a second constraint that says, once I run, I'm going to remember the next state is on. And this guy can have the exec body that says, okay, please go turn on my radio subsystem, whatever that takes. So the point over here is we have this little action that says I can only run if the radio is off, because I don't want to turn the radio on if it's already on. And I know how to turn on the radio. There's a radio off action that does exactly the same thing. Again, he says that my previous state has to be on. I don't want to turn the radio off twice in a row, so only run if the radio is off. And I'm going to set the next state to off. Then, to make the whole scenario hold together, we're going to introduce one more action, this radio idle action. And this guy says, okay, I too want to take as input one of these radio state objects, but my constraint is I want the state to be off. Right? The four modem operations, receive transmit for CDMA and LTE, they all wanted their radio state to be on. Here's the guy who wants his radio state to be off. Why are we fretting with all of this? Now I can write a top-level test action that says, okay, I'm going to do an activity that's going to do a selection between either turning the radio off by calling a radio idle or scheduling a play operation and a receive operation like we did before, okay, because we know these guys will both want them on. So what does this mean? Let's say the first time the tool went down the select, he decided that he's going to do a LTE-RX, right? That guy says, I need the state of this radio state object to be on. But remember, the initial state was off, right? So what must the tool do to resolve that? He says, okay, but I know about this radio on action that knows how to turn the guy on. So he has to run before the LTE-RX operation can run. Next, we decide to do a CDMA-TX. Turns out he also wants the radio on, but the radio is already on. Everybody's happy, right? If the state is already in the state we need it to be, nothing is to trigger. But maybe after that, we come through and we call this radio idle action. And he says, nope, I need the radio to be off to satisfy me. Then the tool can go infer that, okay, to provide that radio off state, I have to go call that radio off action because that's the only guy who knows how to put the state variable into the state that's desired. So this is a way to bring in secondary requirements on your model, right? I think of it as before the receiver and the transmitters can work on either CDMA or LTE. They must first arrange for power to get to the right state. Before we can run this radio idle action, we need to arrange for the radio to be turned off. So that was a little bit on the details of how you can do pre-solve, post-solve, and exec bodies. We saw a little bit about how we do state variables. Again, I'm hoping that what everyone is taking away is how we can think about generating sequences as opposed to writing them by hand, right? Today we can randomize transactions. It's randomization of sequences that is not quite there for us in UVM. What are the different ways a tool like this could run? So if we're a UVM guy, and maybe we have this UVM subsystem, so this model could go into a tool, and however the tool chooses to do this, the tool will be driving all of the VIPs, right? What we're trying to show over here is a subsystem, all running in UVM. There are VIPs for both modems, and there's a VIP for the CPU as well, right? Call it an AHB VIP or AXI VIP, or pick your poison for which CPU you're talking about, right? But all transactional. And now the tool knows what it's trying to do, it knows what concurrency it's trying to do, it knows what order it's trying to do operations in, and it can drive each of those VIPs with the correct transaction at the correct time without us as human beings having to micromanage that for every transaction. Okay, that's great. We got our sequences randomized for UVM, but now along comes my systems guy and says, hey, I've turned your little UVM environment into a subsystem environment and I've stuck my CPUs in there. Can you please test this? And all of a sudden the UVM guy's kind of not happy because now you have to go rewrite all your tests in C, right? Well, one purpose of this tool is to be able to do that translation for you. So once we have the model, perhaps the tool understands how to generate a test.c that can be compiled and run on that processor and coordinate what's happening in the various VIPs to make exactly that scenario happen, but now with the CPU in the loop, right? So we're still randomizing receive and transmit. We're still randomizing whether the audio is using LT or CDMA. We're still randomizing power-ups and power-downs, but now with CPU in the loop, much more complex test, much more power management going on. Perhaps you're turning on and off the CPU as well. So we got some randomization going. We're driving some tests on multiple environments. We probably want coverage. So portable stimulus is very much thought through in terms of not only providing your stimulus, but also your checks and your coverage. The coverage in portable stimulus is derived very much from System Verilog, so the same notions of crosses illegal, ignore. One important thing that has changed is we've changed the name cover group to cover spec. And instead of it being event-driven, right, it's driven based on what variables it's monitoring. So the coverage is currently defined. It's primarily data-centric. It's measuring coverage on variables. Other coverage concepts are being considered, right? Have we covered actions? Have we covered various patterns of actions, right? Various scenarios. Have we done action A followed by action C followed by action F, right? That particular order, I want to measure whether I got it. Have I done all of my data paths? Have I used all combinations of resource allocation? So the other things that portable stimulus let us bring in to the coverage model. So if we go look at the details of the coverage spec, I probably don't need to teach very much over here, right? It is modeled very much on how System Verilog works, the difference being cover spec instead of cover group. So we have different variables that we are monitoring and different bins that we're setting up and different exclusions that we're doing, right? I don't think there's anything new over here, so I'm not going to walk through the details. Familiar is good. Right? How will the tool monitor coverage? Well, some of it can be monitored when the tool is generating tests. So as it generates tests, it knows which scenarios it did, what order it did them in, so maybe it can give you part of your coverage. And then the rest might be monitored. Maybe we want to see, did things actually happen at the same time? Did we see various runtime events? Maybe a tool will generate the trick box code to go do that, right? So you can monitor what's going on real time in the design. Maybe that's C++, maybe that's System Verilog, maybe that's something entirely different that's running on the target. It doesn't matter. It's a tool problem. But acknowledging that some coverage is known when the test is generating, and some coverage we must capture when the actual test is running. So that was taking us from the block level to the subsystem level. Now let's push on up to the full system level. So this slide is a brief overview of what I'm going to do in the next few slides. So at the system level, we're going to reuse that subsystem test audio codec plus 2 modems at the full system level. But now we have 4 CPUs. The tool has a lot more freedom to go decide who runs what. We're going to add a scenario where we're going to stream a video over Wi-Fi. So that'll involve a Wi-Fi modem, a DMA, and then the display. Then we're going to add another use case, which is sending a text message that has a photo in it, right? And my motivation for teaching that case is to show you how you can do more directed sequences. So we'll show how we can do a combination of a directed sequence of operations that'll then bind to other operations and go infer a bunch of stuff. Okay, so part of it is directed, part of it is randomized by the tool. And furthermore, we'll show that the video streaming wants to use the screen, or your text messaging, it also wants to use the stream, so they'll both lock the same resource, and the tool now knows that it can't do both the scenarios at the same time. It must interleave them somehow. Okay, streaming video over Wi-Fi. Very similar to what you've already looked at, and I'm not going to repeat the stuff, right? So we're going to have a VIP for the Wi-Fi, very similar to the model you looked at for the 2 modems. And it'll be bound to a Wi-Fi component that knows how to receive packets off of that VIP. Again, I'm not going to repeat it. Same thing you've seen. And then the output from the Wi-Fi are going to be packets, I think, that are going to be moved by a DMA that end up going to a display controller. All of this by now you've seen. We can instantiate these components. We can establish pools. We can bind the pools together. All of these you've seen. And then the one more thing we're going to do is lock a resource, right? We're going to lock a resource that is this screen resource. So Tom talked a little bit about the fact that we have both the DSL variant and the C++ variant ways of creating models. So I'm going to talk to you a little bit about what it looks like to code in C++. So we're going to do the display components for C++. So we are defining a class display component. It inherits from some object in the PSS library, right, called component. And he has a constructor that takes a particular form, right? And that form is always this PSS macro that takes 2 arguments, the name of the class we're defining and the name of the class it inherits from. And it does some clever connection with that that's very similar to what's happening in System C. Inside that class, we're going to define an action. And the action is also defined as a class that inherits from the PSS action class. He too has a constructor. And then he has this type decal, right? So the type decal is a way of registering the class with the system. For folks who are diehard C++ guys, think of it as we're simply instantiating the object so the tool knows it exists. From the tool's perspective, he wants to know about the type so that he can infer what to do with it. We're going to define an enum. Now in C++, we've had enums forever. However, to give a tool the ability to randomize across those enums, we need to give it a little bit of help. So we have a macro that wraps an enum that says I'm defining the enum called kind under E, and it has 2 values, a video and photo. Now I'm defining one of these data buffers. We've talked about the buffers before. Again, it's defined as a class that inherits from a well-known class called buffer. And then, previously, we've never had constraints in C++, and now we do, right? So we're saying we have here a random attribute of type kind under E, and the name of the variable is kind. So now that's sufficient information for us to pick up that C++ model and go do the randomization, same as we're doing in the DSL. And then finally, we can give this display component an input that says, I'm going to take some data, and he has a constraint that says that type of the data must be video, right? Because I'm doing this display component, and we have one scenario that's going to send photos from the texting operation, another scenario that's sending video for the video Wi-Fi. So we're constraining which kind of input it's taking for display. So there you have it. This is how you define models in C++. And as Tom showed in his slides, right, they're kind of pretty much one-to-one mapping between the DSL and C++. Folks who are comfortable in System Verilog will probably find the DSL more comfortable. Folks who are comfortable in C++ will probably find C++ more comfortable. Now about the resource locking. So we are defining a resource object, right? So this class screen that is inheriting from a resource object. And then we're putting in a lock that says, I want to lock something of type screen, and the name of the variable is lock, and the binding will connect this screen type to this screen type when we have the pools. All right, so that's how everything hooks up. Okay, so that was my displaying video over Wi-Fi. The main thing I showed you was this display component. And there were two things going on. One, we wrote it in C, and the other was it was locking this screen, the resource. Now let's talk about a completely different scenario, right? So far, much of my examples have been based around the notion of binding and auto-inferring what can talk to what, right? Now supposing I want something that's a lot more directed, right? Some very specific scenario that's going to be under software control. It doesn't really lend itself to just do a bunch of actions that you're going to wire together and then the tool pick out whatever he wants. So for that example, maybe we'll say we plan to send a text with a picture in it, right? Something my wife does all the time, right? Take a picture of the kids and send it out in a text to grandma. So first operation we might do is go take a picture on the camera object, and maybe it produces a photo somewhere in memory. Okay, so I haven't shown the details of this, but we can imagine this will happen. Once that's done, maybe I need to use a touchpad to actually type in the message. Hi, grandma, cute kid. All right. And maybe that is somewhere else in memory, produces another buffer. Well, when I'm doing that touchpad operation, I'm using up the screen. I can't be watching the video while I'm typing in the message, right? We do this all the time. We have to pause our video, go across to the text app, go type it in. So we have that resource lock. And then once I have the two pieces, right, the photo as well as the message, then I can call this action called compose message that will take the photo, take the text, and send it to a modem, right? So the point over here is these three things you want to express that is happening in a particular sequence, because it's all in the software control. It doesn't lend itself to binding inputs and outputs. But we know this comp message action, he will produce a packet that will let someone else worry about where that packet goes. Right? And specifically in an example, we know that there are two modems, and either modem can accept that packet, and all of that binding is already there. So what I'm trying to show is we're going to do well-specified part of it, convert. So what does it take to do this? For the touchpad operation, we know we're going to output this message object, right, this buffer. But we also know that we're going to lock the screen resource. That's just let the tool know that he can't do the capturing of the text message at the same time as when he's streaming video. And then what about defining the actual action itself, right? So we're going to instantiate a capture action. This is the guy who knows how to take the photo. We're going to instantiate an enter action. This is the guy who knows how to let you type in a touchpad and create a text message. And then we're going to instantiate that compose message operation, right? The thing that's actually going to send the message. And then over here is what's important, right? The capture operation knows it's going to create a photo, but he has no indication of where it should go. Similarly, the message enter action, it knows he's going to capture some text, but there's no conversation of where it's going to go. These are so-called explicit binds, right? We're saying, hey, please take the output photo from the capture and make it the input photo of the send operation I'm about to do. Please take the output message of the enter operation and make it the input of the send message thing. It's almost like connecting together modules in System Verilog, right? We're saying what must go where. And then we're going to define an activity that says, okay, fire the capture, fire the enter, fire the send, and those things will have to happen in that order, and the bindings will cause the data to be flowed very much under our direct control, right? Over here we could put in a select or we could put in a loop, but it's very much we're defining what has to happen, not leaving the tool open to go do whatever it wants. However, once the send creates a packet, it is bound to either of the modems and it can transmit however it needs to. So now it has many options on where it can go. So now let's try to connect all of these things together. We could bring in our voice scenarios, right? Now we're at the full system level. We can do the voice scenario, 2 modems, audio codec. We can do our texting scenario where we're taking a photo, taking a message, and sending it out. So that also uses the modems. And we can do our video. We're going to watch video or Wi-Fi. And we can throw them all at the tool and say, please do them all. What does that take, right? So at the top level, the point over here is how easy it is to integrate these scenarios together once you have them. So we've got to do our imports to bring in the right packages. We've got to do our instantiation of all the components. We've got to do our pools and our binds to connect up everything the way our design says it should be. But then at the very top level, we're going to say maybe our activity is, for 10 iterations, schedule, playing something on the audio codec, receiving something on the either one of the 2 modem VIPs, playing something on the video codec for the video or Wi-Fi, and a message, right? And the tool is being told, go kick these all off, figure out how to schedule them, and the tool worries about the concurrency. The tool worries about how to order sequences, so it's randomizing the sequences. The tool is worrying about the resource management so that we don't try to watch a video and type in a message at the same time. And this is far beyond what we can do with a UVM sequence today or a C-test today, and that's where the power of the tool is coming from. So once you have all of this, the tool is off. It's free to go schedule all kinds of things. Maybe it does them serially, maybe it does them in parallel, maybe it does some combination, but it must always follow the rule that there was only one screen resource. So either it is being used to view video or it's being used to type in a message.
We're going into a Q&A session with the panel, so hopefully we'll open it up to the floor and you guys can come up with your questions. So the panel, other than the presenters you've already heard today, Ferris started us out, the chair of the Portable Stimulus Working Group, also part of Intel and a verification lead at Intel. Sharon Rosenberg is from Cadence. And he's a solution architect at Cadence and been heavily involved in the Portable Stimulus Working Group. Srivatsa is with Synopsys, also a member of the Portable Stimulus Working Group. And Karthik, another participating member in the Portable Stimulus Working Group. And of course, Tom, who's also the vice chair of the Portable Stimulus Working Group, an active member that you heard from today, and Adnan, another active member that presented as well today. So I'm Larry Melling. I'm with Cadence as well, and I'm going to open it up, to questions. So if you have questions, come on up here, and maybe to get the ball rolling, I'll just throw something out to the panel and get us started. So from your guys' perspectives, how ready do you feel that the industry is for portable stimulus?
So I guess the question is ready versus desperate, right? I think that what we've seen is that there's enough interest in the tools that already exist for there to be a need for a standard in the space. I think that it's been demonstrated. We did a big analysis a few years ago to determine whether or not it was worth putting the standard out, and we came to the conclusion that it was. So there is a need for this sort of thing. I think what we're going to find is the sort of the mindset, as I mentioned, of thinking declaratively versus procedurally is going to be something that's going to take a little bit of time. I think once you make that leap, you'll find out that the language that we've designed is pretty straightforward in terms of being able to implement it at that level. But getting people to think about it in those terms is going to take a little bit of education, I think. So better to get started sooner rather than later.
Yeah, one more comment about that. Like 7 years ago, when we would go to users, and the visionary ones would say, we want the software guys and the hardware guys and all the platforms to work together. They will introduce themselves to us and then introduce themselves to each other. That's how it works. And now when you go out there to user, when you're being called, there's already some plan, concrete plan. They know each other, they discuss. So these changes are taking place in the industry And this is a very good time to introduce the standard, because some of these came up with their own solutions, good, bad. They want a more commercial solution, a standard solution. So this comes in a very good timing from industry point of view.
And let me provide a different viewpoint onto this that is from you guys' standpoint, right? How many people love to write a test case? Better still, how many of you love to maintain those test cases across generations? That guy, hire him. Or shoot him. I'm not sure which one. How many times do we rewrite the same tests over and over again from unit to subsystem to full chip, right? We're just doing the same thing over and over again. That's why we need it.
Yeah, I want to say one thing. I just want to put a spin of reality on the how dare you know on what we're doing and the adoption possibly. It's very important to be humble. So what I mean by that is there's great work being done here. There are significant problems and motivations that we're after to solve, but it also pays off to be humble. Any of you deals with 4 or more activities. If you're in verification any single day, you're debugging, you're checking, you're writing, tests, you're doing coverage, and this may not be your thing. Even UVM sequences may not be your thing. Writing tests may not be your thing. So if you consider, writing stimulus to be 25% of a set of activities across, everything that's done in verification, and then you consider portability and reuse to be even a smaller subset of that, it really takes you to be the agent of change in every team and every company to actually get the productivity and quality. So we believe this is an excellent direction. We believe we're solving a fundamental problem for productivity and quality, but it takes all of you to actually make it happen and make sure that it doesn't get lost as noise. Because if it's a subset of that 20% or that 25%, it will be just a niche thing. It will not happen. Okay, so it takes all of you.
Okay. Again, feel free to come up, but I'll take off of that and kind of go to the next question. So, what would you recommend to a user that wants to consider PSS? So, taking your point, Ferris, and saying, hey, it's going to be, the users that are actually going to make it move forward. What would you recommend, they do to, look at adopting PSS?
Let me try to answer that. There is the dilemma. PSS 1.0 is not out there. By the way, we have the beta out. So, first thing, read it, give feedback to it, etc. It's very nice that we all speak in the same language. Even, this tutorial, it's actions, activities, behavioral model. It's the same thing. Maybe some of you are worried. Don't worry. These concepts are being used. It's not a standard yet, but are being used out there. They're proven out there. Now the question is, maybe a spin on your question, should I adopt it right now with the existing technology, or should I wait? Feedback I can provide as much as I can, reading, analyzing. And this is a dilemma you should all take into account, right? Maybe with existing technology, you can leverage things right now. And if it's simple enough to migrate eventually to the PSS, which there is a beta for it, you should go for it. It's not a throwaway, as opposed to use a less manual approach and then throw it away because PSS is coming. So each one of you have his own probably dilemma out there, whether to adopt existing tool or to wait for the PSS. Just look at where we are, what can be reused versus what you're using today. Someone asked about the usage examples there. We'll try to provide them as much as we can so you guys can judge, make sure you are using something that could be migrated into this concept that we're about to bring out with PSS 1.0.
I want to add a twist to that. The first thing is, I've been a verification engineer for a long time, and I guess as you see many people, there are some people doing block level verification. There's some people doing top level verification. Some people doing system level verification. if you look at all of this, what you'll find out is there's a common thread of a certain number of paths being exercised through that device. Okay. And if you go back and look at your own devices that you're working on, you will find that common thread. I would suspect that if you probably sat down to analyze how much effort is being made, you may find that it's being rewritten multiple times. The most important thing I want to share here is that that portable stimulus can help you save a significant amount of that effort by writing it once. Okay, the same intent. Maybe you might wind up constraining it different ways in different environments to do different things. Maybe you have a few more test cases at one level versus the other level. As Tom earlier said, this may wind up replacing your virtual sequences. But the key thing is there is a certain amount of cost-benefit analysis that you probably have to sit down and do. And once you do it, you'll probably hit the conclusion, wait a minute, this is going to pay off.
See if I can bounce off of Srivatsa's words, saying the same thing another way. What do we say to the users? Where are you having the most pain, the most expense? Where are you having to spend the longest time writing test cases, writing checkers, getting coverage, and having to do it over and over again? Wolfgang Rosner from IBM was on a panel very much like this last DVCon maybe. And he said, to adopt this technology, we need both short-term ROI and mid-term ROIs. The short-term will be pick a problem that you have right now that's hard, that you don't want to do by hand.
My name's Eldon from Synopsys. I had a question about the kind of the context of the PSS solution. Is it based off of other fields, maybe software, or like where does the inspiration for PSS come from? And maybe are we going to pull in inspiration from maybe like software engineers?
What it came from initially actually is tools that are already out there. Right? So when we started this effort, we kind of looked at that. We analyzed the market in a lot of ways. When it actually came time to start working in the committee, we solicited donations from companies that already have tools in the space. So Mentor and Cadence made a contribution. Breaker contributed to C++, which went through some iterations to become now the C++ version of DSL. And right, so I wouldn't say that we pick things from thin air or said, hey, what would be the most awesome language ever? Although this is pretty close. We said, what are the capabilities that have been demonstrated to be useful, and how can we create a language that makes it easy to specify those kinds of things? So we are taking advantage of inheritance, object-oriented programming, extension, all those kinds of things. But as I said before, it's a declarative language, so that's kind of a new thing. It's not quite assertions, but it is declarative, and it allows you to do some analysis before you go and generate the tests, and so there's a lot of good stuff there too. So.
Okay, so yeah, I'll address more of the concept, where the concept's coming from versus who and how they came. So I think the realization came with that specifically in system level, but you can see it in subsystems as well. You have different randomization challenges. So two devices can program to talk to one each other if they, I produce the same data that this consumes. If there are enough resources to enable that communication in the system, if the power modes is up, these are the challenges of creating system level scenarios. They're different. It's like we're creating in UVM, we're creating those virtual sequences. They're not the most sophisticated system level sequences. We don't have enough, cycles for really sophisticated scenarios. But when you try to do with firmware and software, yes, there is. There is so many resources that need to be split. There is operation modes that needs to be figured out before you can even do something very simple. It takes a lot of time. These different challenges, right? And this is where it's all come together, the declarative notion of every action, every piece of behavior would say something about, oh, I need these resources. I need this operation mode to be like that. And then we sort of generate the virtual sequence automatically and sophisticated virtual sequences that will take resource into account and, everything that we mentioned and was shown here today. So this is where it all came from. And of course, in many subsystems, this is, the reality today. It became more and more complex. So That's where the declarative, and, someone asked about sequences. Yeah, you can call them in various ways, right? You can import them and call them. How do I wrap a sequence? But these dependencies, these composition rules is the difference. If I take a sequence in UVM and I just wrap it and I just call it now in various ways, okay, that's randomization. You can do that randomization with sequences as well of UVM. But if I say this sequence requires 1 or 5 DMA channels, depends on this, and it requires either a master or a processor to call it, to use it, right? Then now when I run those sequences randomly in loops, fork and join, now the system can realize things about it. What is legal and what's not. It can do the kind of things that we in UVM typically do with our own fingers and keyboards. So this is where it all came from. The declarative notion that's going to help us and automate things further.
So I think in a way this question also relates to maybe what was asked earlier, right, in terms of, so you're asking about what was the motivation to come up with this standard. And I think that understanding this will also help in maybe, I think, deploying and adopting the standard in corporations, right? So the way I look at this is it really enables system level verification for a product to be done in a very different way. So it's not that it's not been done today, right? We're all engineers. We have this approach of take a problem and solve it, right? So we know that something needs to be done. We try to do a local, minima and try to find out a reasonable way of doing it, right? That's what we are into. So we do this today. It's not that it's not being done today, and it's being done in different teams. Maybe the same information is being used in different ways. So it's happening today. But I think what the motivation is that kind of came here is, if you take a step back, you see a lot of these information being exchanged across teams, a lot of inefficiencies that you can reduce. You can enable a very different way to model your verification intent when you are trying to do system level verification, which is maybe not possible today, right? So I think that's really the motivation. And indeed, I think it is software finally, because if you look at how a system is finally put together, of course, you have the hardware, but it is the software that kind of enables a lot of interesting and complex use cases. And sometimes it is not possible to exercise all those use cases till the very end of your final verification cycle, right? And if you can do that early on with some sort of test software that you can generate from an abstract verification intent, I think it helps you a lot.
If I understand your question correctly, I think what I heard is, have you borrowed something from any computer science applied or otherwise theory, or are you planning on doing so, right? And I'm pretty sure every one of the my friends here, the vendors sitting around, in their own tools, they probably did, right? And they probably did some advanced techniques that would not be disclosed, right? What matters is not so much that. What matters is, if we think we borrowed something, if we think we will be adopting something, are we presenting it to you for your problems in a natural way for what you're trying to solve, right? So if you look at the approach, you can obviously say, well, okay, there are formal techniques being done under the hood, right? And that applies both to, the design as well as the software field. But does that, matter to you as a user so much that there's formal analysis done under the hood? No. What you care about is the tool can actually give you the results based on its formal analysis, gives you the coverage based on its formal analysis. It doesn't matter what kind of formal engine is under the hood, but it's actually giving you the results you care about. So I think that's how I understood understood your question, but it's not easy to answer. Thanks.
Yeah,
Next one.
Maybe one more thing about the visualization that we're using in the slides. We had discussions maybe to adopt UML activity diagrams. Eventually, maybe we converged into these activity charts anyway. So maybe that is something you can say that we were looking at, and it's going to be, as someone asked as well here, it's going to be interesting as well, because the tool, as Tom said, could generate multiple different graphs, different parallelism, different resources are being used, totally different activities to complete what you asked for. And now you want to visualize and see, what did I get? Do I like it or not? So UML activity diagrams may be inspiration. We're not committed to it.
Hi, Anthony Wood here from Imagination Technologies. I've got a couple of questions. First one's a sort of technical one that's perhaps a shorter answer that one of you could answer. The other one's a bit longer, and I would be interested in all your views on it. So, I mean, the first one is really about the way that in the tutorial it was sort of some of the examples gave sort of legal stimulus or like there was one where you would power off completely and then power on and do some other stuff. But you wouldn't want to do that all the time with equal weightings. So it's just a question about whether there is ways in the language of controlling the weightings, or whether it's just a legal thing. Yeah.
It's still work in progress. We have primitive form of weights in the form of constraints like distribution weights like system Verilog. But the fact of the matter is there's a number of topics under enhancement still. And one of them is enhancements to random selection. If you look at the announcement for the beta release, right, you'll see that, enhanced random selection is one of them. So perhaps if you could submit to the public forum, anybody can access it and submit to it. Certain things that you see are missing would tremendously help us out close that gap for the official release, for the 1.0 release.
So just to be clear, there's nothing in the standard currently that would preclude us from adding that kind of thing later. So one of the things we have to discuss is where we're going to draw the line and get 1.0 out and then start working on 1.1, right?
Sure. Okay. So yeah, well, just looking at the presentations, one of the things that strikes me is that I kind of like to have tests that are relatively uniform in length, and it seems that with the random generation, you could have very wildly different test lengths. So that's also something that might be of interest there.
Let's also say why that's important. It was explained several times that that's important to get various flows you have not thought through, and the tool will be able to, based on rules, to kind of create for you. But that's quality value. The other value is when you go from platform to platform, the tools will be able to say, I'm going to do a shorter partial specification or inference for a partial specification because I'm running on simulation and it's really slow. Okay. When I go to emulation, I'm going to do more. Okay. So part of this is leaving it out being explicitly specified, right, and being controlled by a target platform is something you need to think about. So when you write when you write your model and then you write the scenarios or the tests on top of it, you really have to be careful not to put an assumption of the platform in what you're writing. So your statement, you just need to think about it a little bit more.
One more comment about that. You can model the latency of each action and control that. So you can model even based on the input. You have an input of the data. Maybe it takes me this amount of time to process this amount of data. Now I have the latency. Now I can put it as a constraint. If you model it, but it's your modeling, you can have it as a constraint. I want a short test. I want a long test. I want these kind of selections. So the input is there in the semantic. Now it's a matter of modeling, and there's users that have done that with these concepts. So it's part of it.
And just to finish that off, also trying to get graph-based coverage is also something that might be of interest to me and that sort of thing. Right. So anyway, that was the short question. The longer one is in module level tests, let's assume module level testing, the block level test, that they we attempt to get, explore the full space on those, and then at higher levels, subsystem levels, you might not expect to get explore the full space. We do have occasionally you get bug escapes at the module level, and because the tests at higher level are written independently, they're exploring different. The stimulus is different, so they're exploring different space, and they can expose holes in the verification down at the module level. Now, obviously, this is a really interesting development, but you're kind of getting rid of that independence. You're kind of using the same stimulus for both of them. So if there's a problem with it, that's going to go all the way through. So I'm really interested to know what you guys think about that aspect of it.
So there's a couple things going on. So at the module level, you're not just randomizing the scenario. The semantics of the language are that for the data objects, you can actually randomize their contents as well, as I showed. So you can control that as much as you want. So while it is true that you could have a bug escape at the module level, I'd say it's probably less likely using portable stimulus because you're going to get more randomization at the block level than you would have even using EVM, right? Just because there's other things that you're exploring for. When you get up to the system level, you can tweak that as much as you want. So if you really, if you don't want to look at all 16 bits worth of whatever, right, you don't have to. But a lot of times the data, the things that are going to uncover the bugs at the subsystem or the system level are those interactions with the other things going on. And now with portable stimulus, you're more likely to uncover those things, even though you're using the same behaviors, you're using them in combination with other things that are going on. So you may have, if you have you may have a DMA engine right now, instead of focusing on how it's interacting with one thing, it's how it's interacting with everything that wants to DMA in the system. So you're going to have lots of other kinds of things going on. So I think while there is a common mode problem in anything, I think the value is that we're taking what used to be considered a good thing in constrained random data in UVM, where you sort of have the tool pretend to be the independent verification team by doing things you hadn't thought about. Now we're sort of taking that to the nth degree by combining all the other things going on. So I think it's less likely that that's a problem. It is there's always a problem that there's a chance a bug is going to get out, but I think it's much reduced using portable stimulus.
Yeah, let me agree with Tom and say when you try things on the model level, you can do random stuff, right? You have big test bench, you can, no memory requirements, no resource requirements, it's all test bench, all synthetic, try. That's good for you, by the way, right? Exhaustively, out of the randomness, get your coverage, you're great. Things run faster also. Now you move to the system level, there's context of the system. More constraints are coming from the system. Here's the address space. Here's resources that you have. It's no longer a synthetic test. It's a specific constraints coming from your system level. And this is where you might find out that though you do very exhaustive random testing on the module level, you never tried the one thing or one scenario or a few scenarios that you're trying in the system level. That's a different path, right? I put it in the context of a full system. Now I'm trying different system level use cases. So, but now we contribute. PSS allows you to do that. Put all the constraint on the subsystem level. As Tom said, do exhaustive testing on that level. When you put things in a full system level, now you get all the constraints that are coming from the system. By the way, it could be totally different use cases, right? Not anything close to what, or very small subset of what you tried on the subsystem level, but it's totally different context right now. And this is where the bugs comes out. I mean, if you have redundant test bench, you might find other bugs anyway. But we allow you to choose, and we allow you to put a system level context. And once you find the bug, now take that to the subsystem level to see where the issues for debug purposes. So I think we provide both paths, both contexts context and allows you to
But
move
the
between
reason
them.
why we would have missed the bug could well have been an invalid constraint at a module level. Right?
It's an interesting
and then
question.
That goes all the
You're-
way through.
It's an interesting question. You're saying there's a bug in the model or part of the model that was delivered by the IP. In current practices, we have folks at the SoC or subsystem separate from the IP. These guys write in your VM. These guys write in C. So the teams are separate and they're using different techniques, different languages. So the redundancy is helping the next team in line or the downstream find bugs because they're using a different path, a different technique to do it, right? And if I understand the question correctly, right? And part of the answer you heard is correct, which is just because the same model is going to be at both levels doesn't mean the test generator is going to be exactly the same. So you'll get a different test generated because you'll add more IPs, you'll add more modules at the system level. So the chance of finding bugs is still there. But the question I'm going to bounce back to you is, why is it actually something we want to mask? If there is a problem with how the IP understood the behavior for their IP or their module, right? Why would we not want to expose that in the model they're exporting to everybody or they're delivering to everybody, right? Now at least we have a chance to see if we find a bug in how they interpret their behavior, then it's in one place, we can all discuss it, and also discuss it in the context of other models coming next to it from other IPs. So it's an interesting question, but I think it hides a different problem. It hides a problem that if I get a model from an IP and it has a bug, it actually indicates that there is a problem, possibly even with the IP sequences.
So let me give you.
Right, the other. Oh, sorry. Go ahead.
Let me give you a practical answer also to your question. I agree with all these guys saying, right? Hey, we're building these tools. We're very excited about it because you have wonderful tests. What happens in reality? You're going to build these IP models. They search a lot of things. System level. Typically, I'm seeing these models over-constrained, right? Because the system level guys say I can't sort of deal with all the wheel combinations. So that's making your problem worse. But then we're not going to boil the ocean. We're not going to change your world. At some point, you're going to say, okay, I ran those tests. I still want to run my system tests, but now I want to call my software routines. Right? You have software functions that trigger each of these operations. We don't have to do them all, but from the IP model. And then you'll be back to running tests at the system level you're running before. You have that cross-check. And with any luck, we flush all the problems out over there for exactly the same reasons. That make sense? So your system test, you might drop out the module block, the models for the modules, and replace them with models that are calling your software routines.
Yeah, and the other thing, just to expand on what Farah said, so the ecosystem that at least I foresee, and I think everybody is pretty much in agreement, that IP providers, whether design IP or verification IP providers, will include with that the portable stimulus specification, the actions that the block will do, the requirements for them, et cetera. So as Farah said, it's kind of up to the IP provider to make sure that those things match. And if they don't, then when you find you will find a problem because there's if they don't match, there's a bug, it'll be uncovered. And as everybody else said, when you bring it up to the subsystem and the system level, you're creating more unique tests. So you're more likely to find more stuff. You're more productive by just the sheer number of tests that you're going to wind up generating. So I think that's how it's going to go.
Just offer one last enhancement to my answer would be, I have this problem today even in sequences. When I take IP level sequences and reuse them up, right? Because of reuse, I get bugs in what I'm reusing. And what I try to enforce is not just the positive, but also the negative space. If you're not supposed to do this, I also code that up. I actually write it and check for it, right? So if you say your IP does not support error correction codes, ECC, right? Or corrects it in a particular way, but not the other way, or handles, 1 bit, but not 2 bit, I'm going to do the negative case as well and try to see if it does or does not, right? So there's that problem. It still exists as a reuse problem no matter what, right? And there are other techniques to go after finding these issues.
Just one last thing from my side, right? So I think what you said also applies. I'm trying to kind of counter what you're saying with another scenario. May seem a little stupid, but yeah, just bear with me. Suppose you have two parallel block level test teams, right? You have one DUT and you have set up two independent teams, both doing block level verification, right? UVM, SV. Of course, there's going to be a lot of duplication. And of course, the first team is going to find some bugs that the second team misses, and the other way around. Possibly, right? But the thing is, here, so if you say that by doing this independently, we are going to detect more bugs, then it is just, it's not by design, it's more by, by luck, right? Because you have two independent teams reading the same spec. Maybe they interpret it differently and they come up with slightly different tests, and in the process, the spec becomes better. But this whole thing happens, I think, by at a cost of, at a huge cost. And what I think is happening here, it's similar, except you're replacing, instead of having two, block level test teams, you're having maybe something to do with block level and system level, right? So there is a possibility that these two teams now can reuse certain verification intent, and in doing so, it might happen that some bugs maybe that could have been caught in the current system may not be getting caught. That's true, but I actually think it pays off more because you have a common spec now, but which the two teams can kind of look at, and I don't know. Do you get where I'm getting to?
I think I understand what you're saying. Yeah.
Okay. Yeah. Okay. Thank you.
Good. Thank you. Do you have a question?
Yeah, just kind of a low-level question about the DSL language. That's what it's called. Yeah. Okay, what does the D stand for? That's not the question.
Domain specifically.
Domain. Thank you. Okay. I'm curious about. So you showed us how we could express states like power states. So that made me think. Okay. Well, how do you? What does it look like if I draw a state diagram with bubbles and states and variables and transitions? Does that translate directly into the language where each state is a class or an object or something like that? What does it look like?
Yeah, go ahead, Sharon. Okay. So states are another form of flow object. There's only one per pool. So everybody that deals with a particular state is updating the state of the variable. It's not that it translates directly from a traditional state diagram, but you could draw a regular state diagram from what's going on. You can see everybody that writes to it. You can see the scheduling between them, and so from that you can figure out what's going to happen to that state variable. The only rules really are that you can't read and write to a state variable at the same time, and you can't do multiple writes to a state variable at the same time. Otherwise, you get a race condition. So given that, the rules are sufficient to be able to analyze a model and figure out what the state transitions actually are for that variable.
Okay, so
That didn't quite answer your question, but I think the answer is yes. It is possible to model state machines where you have actions for each transition for each state.
okay,
There are multiple ways you can do it in the language.
is that with constraints in the state definition? I remember there's like pre.
Oh yeah, if you wanted to have an action with a constraint that says if the current state is this, the next state is that, yeah, you can do that all day long. Yeah.
Okay.
Go ahead.
Thanks.
You want to say something, Sharon? Sorry.
Well, we explained it in the tutorial, so I guess we need to repeat that. But you can basically define what is a legal state. Okay, so you put it in constraints, and now you can. Oh, I want to go to all the states and ask the tool to take me to all the states. Now you can also have constraints about what transitions are legal. Okay, different kind of constraints, and you can look at it as input and output constraints, right? I can have constraint from this state to that state value, right? This state value, these are legals. These are only the legals, and that's provide yet another layer of constraint. If you have, sometimes you can go from any power state to any power state. Sometimes, so you just need to describe what is a legal power state, and it will make sure it takes you only to legal transitions of legal power state. Or you can say, no, I cannot just jump to whatever power state I want. Maybe I can just go one power level up or power down, or I always go active and then go to some power off. So these are constraints on the action, which is the transition of the power state. So between these two, you kind of, that's the principle, right? Define one class, which is a state. It has constraints about what is the legal state. And if you have any kind of dependencies on transitions, define that. That's an action of a transition with constraint between the input and output. And that's it. Now the tool can play with it.
Logi Ramachandran. I have two questions. First one is the list that you put on the screen there. Two bullets especially. One, the last one says conditional code processing. Are you talking about preprocessors here?
Not exactly.
Okay.
That's one way we may choose to do it, or there might be other options.
Okay. And the other one is parameters. So I guess it's something similar to system verilog parameters that you're looking at?
Yeah, like type parameters, that sort of thing.
Okay. The second question I have is, this is more based on Tom's comment that VIP vendors would start adding a DSL-specific set of routines to the VIPs and also the IPs. The question is, how do you ensure interoperability in that situation? Because one of the advantages we have with VIPs today is I could buy two VIPs from two vendors and it just works, right?
Mm-hmm.
How does this keep that interoperability going forward? So that means when you make a DSL routine for a VIP,
yeah,
I have to make sure that it is going to be working with another VIP from another vendor who may have a completely different data stream type or whatever, right?
Yeah, so that is something that would have to be managed. Packages is one way that you could do it. We may have to look at defining some way of massaging a packet from here to a packet from there, that kind of thing. And
that will be done by the customers who are using the two VIPs from two vendors?
Potentially, yeah.
Okay.
I mean, it's the same sort of thing now, right? With if you provide somebody a UVM sequence, there's going to be a transaction type that they have to deal with, right?
So just one comment. You can have a translation action, which receive action of one VIP and translate to the action of another VIP, and this will be called automatically. So even if a VIP vendor created his own config with his own field names and another constraint, someone created a different, but they're the same. It's the same dependencies. You can create a translation and the tool will figure it out as it does. So it's a translation that doesn't create any code. There's no exec block associated with it, but you can create that very easily.
So you input one data stream type, output another data stream type.
Exactly.
Thank you.
Hi, my name is Sanjeev from Juniper Networks. I was a little confused on the C test that gets generated. So suppose I want to rerun those C tests on post-silicon, or are you guys going to specify like a board support package that can run any of those C generated tests? Is that part of the standard, or is it going to be every vendor generates a generic test and then we have to do the support package for each of these vendors?
So let me try to, I'll just restate my understanding of the question. And, so you have maybe a full platform that you want to test. And in order to execute these, the final test code, there has to be a lot of interaction between, setting up the hardware in a certain way, programming registers, interrupts, and so on and so forth.
And probably like thread package and coordination
sure.
across the threads.
Sure. Okay. So there are some capabilities that may be available on the environment, threading, for instance, even things like printing to some terminal and stuff like that, right? So your question is it expected that the end customers prepare this, or is it going to be somebody else? That's what you're asking.
Yes. Is it part of your standard that you're
Sure.
releasing that so that anyone can just rerun the C test if they implement the support package?
Sure. So I think part of the answer will be tool specific. That's what I think. When it comes to providing a customer an environment in which the tests will finally run. You can imagine there is going to be a lot of libraries that need to be maybe linked with, and quite possibly the vendor who provides a tool will also provide these libraries. But the other part of your to the answer that the question you're asking for is indeed we are working on some enhancements to the standard that will allow a customer to capture the interaction between the test software and the hardware. So this interaction we should be able to capture in a way that the customer can reuse across different environments. So that's one of the bullets here. But yeah, I won't go more into it because it's really work in progress. Yeah, I think Sharon.
I'm not sure. Maybe there is confusion with my understanding. So let me just say this. Maybe this will clarify to me or to you. The firmware routines that you're eventually going to call are your own firmware routine, the user firmware routine. We don't know. That's not part of the standard. That's not going to be provided under the standard. And if it will not work on your specific system, right? So the way we start, and of course you have the platform and you have your compile and compilation chain, which we're going to use. We're going to, just use it. That's the nice thing. We don't ask UVM users to change anything. When we don't ask the C user to change anything, we're just going to play the test, write a role of creating the test as if you created them with your own keyboard and fingers. So now we're going to look, let's say we're modeling your firmware right now because we want to create C tests for you. We're going to look at that and we're going to create some actions that eventually going to call your firmware routines, those exit blocks. But how we're going to solve it is we're going to put an action and we're going to capture all the dependencies, because you cannot just call these firmware routines in any arbitrary order and it will make sense. There's resources, there's engines behind them, right? This is where the inputs and outputs are coming into the play. And now a tool can generate a legal C software, like for multiple cores with all the sync points between them that will work. So that's what we're doing. The C code is going to be within your own firmware that you will put in the exec or the import functions that you're going to use, but this is not something coming from us. Now, there is some code that will be coming from a tool for synchronization, for example. Oh, this core needs to wait for that core. That's not something also we're going to deliver. And if that's what you ask, then that's not
right. No, so what I was thinking was, are you guys going to give like a C header file that specifies the API between our low-level firmware and the tool? Because even the firmware, we don't want to embed our function call.
Yeah, as Sharon said, it's up to you to define what that API is in the exec block. So it's beyond the scope of the
We are very generic. Right. We can support any firmware, but we don't provide anything. Yeah. You do all the work.
All right. So I think we're about out of time. And thanks again for attending.